Good afternoon, everyone. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics at Australian National University, and welcome once again to another seminar in our series on various topics of theoretical physics. Just while the last few people are rolling in, I'll just make a couple of quick announcements. I'd like to start by taking this opportunity to remind everyone, particularly students, about the Australian Institute of Physics Congress, which will be held in Melbourne this year from the 2nd to the 6th of December, with a welcome reception, I think, starting on the day before, the 1st of December. I believe submissions for that, for the abstracts, have now closed, but early bird registration will remain open until the 28th of August. If you want any information or you think you might like to attend, there's an Australian Institute of Physics Congress website that you can look at. Shortly after that, in early 2025, will be the 47th annual Condensed Matter and Materials meeting. This meeting we colloquially call the WAGA meeting because it's usually in WAGA. It's a long-term conference that's been held for many, many decades. But this year it will be held at St Lucia's College at the University of Queensland, starting from the 4th through to the 7th of February. The WAGA conference is traditionally very relaxed, with an emphasis on giving students an opportunity to present their work. It has an extended poster session, for example, although you can also give verbal presentations. So for that reason, it's ideal for students, amongst other scientists, of course, working in condensed matter physics or materials who'd like to present. Traditionally, I think the closing date for abstracts for the WAGA conference occurs around August, something like that, I believe. I'm not sure that that's been finalized yet. But now, if you did want to attend or you wanted to present a paper, now would be a good time to start thinking about putting some material together for that. And again, once again, if you want more information, do a web search on the WAGA Condensed Matter meeting for 2025. I believe it's the 47th one. Also, I believe that 2025 is going to be the International Year of Quantum Science and Technology, believe it or not. I'm not sure if that'll be a major event around the world covered by all international media, but anyway, there it is. I don't think the AIP has decided what it's going to do in relation to that, but stay tuned. We'll let everybody know as the time goes on. All right, let's do some physics. So today's talk is by Daniel Leykam on conical intersections and interesting similarities between wave-packet dynamics in the vicinity of conical intersections that mimics the behavior of relativistic spinors. I'm not sure if everyone understands what quantum intersections were. Daniel, of course, will explain them, but they are a fundamental concept in quantum mechanics. They occur when two or more, usually electronic potential energy surfaces, intersect at a point, and locally the intersections look like a cone, hence the name, in the immediate vicinity of the conical intersection. They're very important in a wide range of quantum systems because, amongst many other attributes, they provide a pathway by means of which energy can be transferred non-radiatively from one potential energy surface of a quantum system to another. This turns out to be very important in the understanding of chemical reactions and molecular dynamics. So it's of great interest to physical chemists as well as to physicists. In fact, I don't think Daniel is going to talk about this today, and correct me if I'm wrong, Daniel, but I believe it's now fairly widely accepted that conical intersections are responsible to some extent, or perhaps even to a great extent, for the viability of life on Earth as we know it, because they provide a mechanism by means of which it is now believed DNA molecules, for example, once excited by an absorption of an ultraviolet photon, can dissipate that absorbed energy efficiently as heat through non-radiative decay processes via conical intersections. So it's a very far-reaching area of research. In today's talk, as you would have seen from Daniel's abstract, He'll be discussing some more fundamental aspects associated with conical intersections that are absolutely fascinating, and looking at the relation between pseudospin and angular momentum associated with the dynamics of wave functions in the vicinity of conical intersections, and then generalizing that to a consideration of pseudospin 1 and pseudospin 2 conical intersections. Daniel obtained his PhD from Australian National University in 2015. He has held positions at Nanyang Technological University, the Institute for Basic Science in Korea, and is currently at the National University of Singapore, although within a few weeks, he'll be taking up a new position at the Singapore University of Technology and Design. Since 2022, he's also served as an associate editor for Physical Review A. Daniel's talk today is entitled Conical Intersections and Angular Momentum. Thanks very much, Daniel. Over to you.
Okay, thanks for the kind introduction. So I was wondering what I should talk about today, and I thought it would be quite fitting to present this topic, which is something which I started working on in 2012 while I was still at ANU. And I've been working on it off and on for the past 12 years or so. So some of what I will present today is old stuff, some is new stuff, and stuff I haven't talked about before. So in your introduction, you talked about conical intersections in the context of molecular reaction dynamics. So I'm going to be looking at conical intersections in a bit of a different context. So in the context of two-dimensional materials and related periodic lattice systems. So back in 2012, when I was starting my PhD, there was already tremendous interest in graphene, in particular thanks to the 2010 Nobel Prize in Physics awarded for its isolation. So graphene has many remarkable properties. It's a ultra-thin, generally two-dimensional material. And some of its interesting electronic properties arise from this lattice structure of graphene, which forms a honeycomb lattice of carbon atoms. So after the award of the Nobel Prize, there was a lot of interest in seeing whether we could mimic some of these interesting properties of graphene using other kinds of periodic wave media, including ultra-cold atoms in optical lattices and light-based photonic systems, such as arrays of optical waveguides. And this is summarized in, for example, this review article, which was already published quite a long time ago. So at the simplest level, we can model the energy spectrum of graphene using a type binding model, where we have a lattice of carbon atoms forming this honeycomb structure, and we take into account hopping between of a particle on this lattice. It could be an electron, it could be a photon in the case of waveguide arrays. So we take into account hopping between the neighboring sites to construct a type binding Hamiltonian, which is shown on the left here. Now, as is standard in the band theory of solids, thanks to the translation invariance of this periodic lattice, we can get its energy spectrum via a Fourier transform, which will give us a spectrum of eigenvalues here forming the band structure on the right. So when you Fourier transform, this effectively decouples this lattice Hamiltonian into a set of independent two-level systems, which are indexed by the crystal momentum k. So for each k, I have a block Hamiltonian, which describes the hopping of the block waves between the two sublattices. Since there are two sublattices A and B, this is a effective two-level system corresponding to two energy bands. Now you'll see that the two bands quite interestingly touch at the corners of the Brillouin zone, termed the K points. And these band crossing points are very interesting, and they're responsible for many of the exotic electronic properties of graphene. if we now zoom in and look at what's happening in the vicinity of one of these band crossing points, we can derive an effective Hamiltonian by performing a long wavelength or a Taylor expansion of the block Hamiltonian about one of the K points. And if you do so, you will find a very simple effective Hamiltonian taking the form shown on the right, which simply takes the form of a 2D Dirac Hamiltonian. So it's all the spin matrices sigma dotted with the momentum displacement from the Dirac point P. So what is quite important here is that these Pauli matrices, they do not refer to the physical electron spin. Rather, these are operators which are acting on the sublattice degree of freedom. So they are observables related to the A and B sublattices of the honeycomb lattice. So in particular, if we look at the sigma Z eigenstates, this is diagonal in the sublattice spaces. So we can say that an electron living on the A sublattice is analogous to a spin-up particle. An electron on the B sublattice is analogous to a spin-down particle. Okay. So it's interesting to ask: is this introduction of Pauli matrices, this spin-like degree of freedom, is it a mathematical convenience, or does it have some deeper significance? This question was partially addressed in this PRL paper from 2011, where the authors examined the question of whether this pseudo spin-like degree of freedom actually represents a real form of angular momentum, like the usual spin that we are more familiar with. So to answer this question, the authors looked at the energy spectrum of this effective two-dimensional Dirac Hamiltonian, which is shown on the left here. So you have the two conical bands touching. And quite clearly, this energy spectrum is invariant under in-plane rotations in the XY plane. And as we all know, invariance under some symmetry transformation suggests a conservation law. So for the case of in-plane rotations, we expect to have conservation of some angular momentum. However, if you compute the commutation relation between the orbital angular momentum operator, L, and this effective Dirac Hamiltonian, you will find that these two observables do not commute, suggesting that the orbital angular momentum is not conserved in this model. To get a conservation law, you have to instead consider a total angular momentum J, which is a sum of the orbital component L and a spin component S, which is precisely this sublattice pseudospin. So only this total angular momentum is conserved within this 2D Dirac Hamiltonian, describing the low energy excitations of graphene. So based on this derivation, the authors made this, what I found a very fascinating conclusion, which is that this analogy between pseudospin and real spin suggests that what we think of as being an intrinsic property of fundamental particles, their spin, might not actually be intrinsic, but it might be something which is emergent based on some hidden substructure of space-time, such as space-time forming a lattice with some structure like a honeycomb lattice, leading to spin as an emergent property. So when I first read this paper, I found it really quite fascinating, and this was something I wanted to look into in more detail over the course of my PhD. So two questions presented themselves. One is if this pseudospin is indeed a real form of angular momentum, can we use it to generate other forms of angular momentum, such as the more familiar orbital angular momentum or spin? How do we couple between these different forms of angular momentum? Secondly, this graphene model gives rise to a spin half degree of freedom. Is there a way to generalize this construction to particles which have different spin, such as spin 1 photons, spin 2 gravitons? This is something that we also looked at. So these are the two questions which I want to cover in my talk today. If there are questions at any time, please interrupt me and I'm happy to answer them. Or we can wait to the end if you prefer. So I'll start with the first question. How does pseudospin couple to other forms of angular momentum? This is the question which haunted me over my PhD and spent a few years to try and get to the bottom of. So a simple way to understand coupling between pseudospin and orbital angular momentum within this effective Dirac Hamiltonian is to rewrite it in polar coordinates and in terms of spin raising and lowering operators, like so. So written in this form, we can see that the dynamics generated by the Dirac Hamiltonian HK involve a flip of the pseudospin accompanied by the introduction of a phase winding term, this exponential factor here, which can increase or decrease the orbital angular momentum carried by the wave function. This is, of course, required in order to maintain the conservation of the total angular momentum J. What this suggests then is that if we prepare an initial state as an eigenstate of the pseudospin, sigma z, say in this case s equals a half, then if we let this state evolve in time, there will be coupling to the down pseudospin state, and this coupling should be accompanied by the generation of an orbital angular momentum or a phase vortex. So this is the theory. How do we go about observing this though? So to do this kind of coherent wave packet preparation seems very difficult in the case of electronic systems such as graphene. So we can instead consider photonic systems, specifically optical waveguide arrays. In particular, if we consider the limit of paraxial light propagation, the evolution of the paraxial light beam is governed by this paraxial wave equation here, which takes a very similar form to the two-dimensional Schrödinger equation. The main difference is that the time evolution is replaced by propagation along the z-axis, and the external potential in the Schrödinger equation is replaced by a modulation of the refractive index. This means that if we construct a honeycomb lattice of the refractive index, this will give rise to an energy spectrum and dynamics closely analogous to those occurring in the graphene honeycomb lattice. Quite remarkably, it's been shown that to get this interesting conical intersection in the block wave spectrum, you don't need to rely on a deep lattice described by a type binding model. Actually, you get Dirac points regardless of the depth of the potential, even for very shallow potentials, provided that the lattice has the required honeycomb symmetries. This was shown in this paper published in a mathematical journal. So as I mentioned, then what we can do is we can prepare an initial state with a definite value of the pseudospin, that is up or down. We can then let it evolve in time or z. And what we expect to see is a conversion from the pseudospin into orbital angular momentum. This was done in experiments here published in 2015. So you need to look quite carefully here because it's experiments and it's noisy. But on the left panel, they have the intensity of the initial state, the intensity of the wave function at time 0 or 0 propagation distance. And then on the right, we have images of the intensity and phase interferogram after propagation by some distance through this honeycomb photonic lattice. And if you look very carefully in the interference fringes, in panel D, you will see that there is a fork outlined in the circle. So an up-facing fork. This indicates that there is a phase singularity in the wave function. For the case where the initial state was residing purely on the A sublattice. If you flip the pseudospin of the initial state, so you instead excite the B sublattice, the output state is shown in the bottom two panels. Okay, in the intensity, it's hard to see much, but in the interference fringes, you see that the direction of the fork has been flipped. So it's now a down-facing interference fork, which indicates that the sign of the orbital angular momentum has flipped from positive to negative. And this is fully consistent with a conversion from this pseudospin into orbital angular momentum. Okay. Now it's a bit clearer to look at the simulation results instead, which is shown on this slide. So here we're simulating this experiment, where again we start with a wave packet which is exciting a single sublattice. So it's a definite, it's an eigenstate of the pseudospin with a Gaussian envelope. We then let this wave packet evolve in time for some distance or some propagation distance. And then we look at what state emerges. So on the leftmost column, we have the intensity and phase of the full paraxial wave function. The next two panels, we project this wave function onto the slowly varying envelope, which is described by the Dirac Hamiltonian. This gives rise to a smooth intensity and phase profile in which we can see much more clearly this coupling between the pseudospin and the orbital angular momentum. So in particular, so our initial state was an eigenstate of the spin up. And we see in the output spin up component denoted by psi plus, the phase profile remains smooth. So there is no orbital angular momentum in the spin up component. If we look at the spin down component, while the intensity looks very similar, the phase profile is very different. We see there is a phase singularity here at the center of the beam, corresponding to this generation of orbital angular momentum, which is required to conserve the total angular momentum J. So this means that the the dynamics of this slowly varying beam envelope seems to be fully consistent with this effective Dirac model, indicating a conversion from pseudospin to orbital angular momentum. However, a question presents itself. We have a very nice and smooth profiles when we look at the slowly varying envelope. But if we look at the full paraxial field wave function A in more detail here, we see that it looks very complicated. So the intensity has this rapid modulation on the scale of the lattice potential. So in particular, the intensity tends to reside on the sites forming the honeycomb lattice. In the phase profile, we get something very complicated with many phase vortices, many singularities. So it's not clear then that the orbital the pseudospin is responsible for all the angular momentum present in this full wave function. Perhaps there are other corrections. So in fact, we can write down 3 different forms of angular momentum in this system. We have the pseudospin and the orbital angular momentum, which are associated with the slowly varying envelope of the beam, described by this 2-dimensional Dirac equation. So the sum of Sz plus Lz we expect to be conserved. Separately, we can write down what I will call a microscopic orbital angular momentum. This is the orbital angular momentum associated with the full wave function without bothering with any long wavelength limit or Dirac approximation. This is a well-defined quantity, which is what one would more naturally measure in an experiment. Say, for example, from the force, the rotational force or torque imparted on a particle by this optical beam. So the question then is there a way to get the dynamics of this microscopic angular momentum using this effective Dirac Hamiltonian? The second question is, we see in this paraxial beam that there's a modulation on the scale of the honeycomb lattice potential. So does the details of this honeycomb lattice potential, its shape, its depth so much, and so on, does this affect the microscopic angular momentum carried by a honeycomb lattice wave function? So these are 2 questions which puzzled us for a few years. So we first set about trying to resolve or answer these questions using some numerical simulations. So at least numerically, we can do everything exactly. So we can solve the paraxial wave equation to get the full dynamics of the microscopic wave function A. Once we have this, we can extract its slowly varying envelope by projecting onto the exact block functions of the potential. This will give us the spin up and spin down components, which are governed by this effective Dirac equation. So once we have A and psi-s, we can then just evaluate the expectation values of these angular momentum components and see how they compare. So the results are shown here. So let me just walk you through, say, the plot on the left. So we are plotting here the different angular momentum components as a function of the propagation distance z, or equivalently the evolution time in the context of the Schrödinger equation. In blue, we have the slowly varying envelope orbital angular momentum. In green, we have the pseudospin. J, the red curve is the sum of L and S. And then the thin light blue curve is the microscopic orbital angular momentum of the full wave function. The thick black curve is the microscopic angular momentum when we project the wave function to only the low energy modes. So the two bands associated with the conical intersection. And on the left and right, we're considering different initial states which have the same total angular momentum, but different L and S initially. So what can we see from these plots? So firstly, we see that this quantity Jz is conserved. So it's independent of Z. This suggests that this long wavelength Dirac model is providing a very good approximation to the dynamics of the wave packet in this honeycomb photonic lattice. Secondly, if we look at the microscopic orbital angular momentum, what we find quite surprisingly is that this quantity appears to track the pseudospin, so the green curve, in both cases. So it seems to follow the pseudospin and is completely insensitive to the orbital angular momentum carried by the envelope of the wave packet. So you see, even when as the blue curve changes, there is no obvious influence on the microscopic orbital angular momentum. It tracks the pseudospin. So this was surprising to us at the time. And we wanted to double check whether this result was really trustworthy. So one thing what we decided to check then was what happens if we very weakly break the symmetry of the honeycomb lattice by introducing a weak imbalance between the potentials on the A and the B sublattices. So in the context of graphene, this opens up a band gap. So you go from a conical intersection to two parabolic bands with a non-zero wave effective mass. The size of the band gap is controlled by the size of the sublattice symmetry breaking term. Since the eigenstates are different, we expect then that the dynamics of the pseudospin will also change, and this should somehow perhaps affect what is happening to the microscopic orbital angular momentum. So here we show now numerical results for the case of a very small asymmetry between the two sublattices on the order of 10 to the minus 4. So this should give something which is numerically negligible. What we see is, okay, in one case, the plot on the right, the top right, in one case, we see what we expected to see. That is that the small perturbation has a very weak influence on the microscopic orbital angular momentum, and the dynamics remain almost the same, tracking the pseudospin. But for other initial states, we get a very strong sensitivity to this very weak perturbation. This occurs for different values of this occurs for both zero and non-zero values of the envelope angular momentum, and for different values of the pseudospin. So this was puzzling to us. how can we reconcile this very weak perturbation with this very big change in the angular momentum dynamics? We were not sure whether this was an issue with our numerical solution or whether it meant simply that the Dirac Hamiltonian is not able to adequately capture the details of the microscopic angular momentum in these periodic lattices. So the answer to this conundrum came after a lot of failed searches. Eventually, we found out that this question had been partially addressed in the earlier condensed matter physics literature. And the answer partly rests in the effect of geometric and Berry phase effects on the eigenstates of periodic potentials, which was debated from the 90s for 20 years or so. So how to understand this dynamics of this microscopic angular momentum? Well, the obvious way to settle this question is to simply rewrite this orbital angular momentum operator in terms of block wave eigenstates. This is, however, easier said than done because the orbital angular momentum involves this position operator R, which is ill-defined for periodic block functions. So if you try and evaluate these integrals naively, they don't converge at all. So you have to do this analysis very, very carefully. But if you do so, what you'll find is that this microscopic orbital angular momentum can be decomposed into two terms, M1 and M2, which I will call a bulk term and a surface term, because it arises from integrating by parts. So the bulk term, M1, this is similar to the bulk term investigated in these previous papers. It involves not just the orbital angular momentum of the envelope, which is this first term here, but also an additional contribution arising from the Berry curvature of the energy bands, this omega term. And this Berry curvature is acting as an effective magnetic field, which imparts an additional rotation to the wave packet, generating additional orbital angular momentum. So this is M1. In addition, we found a new term, M2, which we call a surface term, which only arises for the case of coherent wave packets, which occur, for example, in photonic systems. This second surface term is proportional to and so the first term, the M1 term, the strong sensitivity of the angular momentum dynamics to this small sublattice symmetry breaking arises because the Berry curvature at the Dirac point is highly singular. Here we have the analytical expression for the Berry curvature as a function of the gap size delta and the momentum p. So you see that if the gap is 0, the Berry curvature vanishes. If the gap is non-zero, we have a non-zero Berry curvature, whose peak value diverges as delta gets very small. So for a very small sublattice symmetry breaking, we get a very large Berry curvature, which can impart a very large additional rotation to the wave packet. So this explains this very strong sensitivity to this very weak perturbation. So now that we have this expression for the microscopic orbital angular momentum in terms of the block functions. We can compare the numerical calculations to the predictions of this very simple effective Dirac model. And we get this very beautiful agreement between this two-band model and the numerical results. So for all the different kinds of initial states, the theory and the numerics are lining up perfectly. So this resolves the first question I posed, which is firstly, the pseudospin does contribute to the microscopic orbital angular momentum carried by a wave packet. And second, which I find quite remarkable, is that this contribution is actually independent of the fine details of the lattice potential. All that matters is these two derived parameters, the gap size, delta, and the cone angle, VF. Once you know these two parameters from which you can get out of a microscopic calculation, you can fully describe the angular momentum dynamics of the beam just using this much simpler Dirac equation. Okay, so this is the end of the first part. If there are any questions, I can take them now. If not, I can move on. I guess I should speed up a bit because
No, you're okay. Take your time. I think we're going to leave most of the questions till the end, if that's okay. Daniel?
Okay.
Yeah.
I'll try and go a little bit faster.
No, it's okay. Take your time.
Okay. So the second question we want to look at then is, do these observations generalize to particles which have higher or different values of the spin, in particular spin 1 and spin 2? So at least formally, you can take this effective Dirac Hamiltonian and replace the Pauli matrices with spin-S operators, and like so. This will give you a family of effective models for different values of the spin. The most interesting difference arises depending on whether the spin is integer or half integer. When the spin is integer valued, the projection of the spin along a given axis can be 0. This corresponds to the presence of an energy band that is completely flat, sandwiched between the other conical bands. So you see this for spin 1 and spin 2. So this is fairly nice result, which can be obtained from this effective, this generalized Dirac Hamiltonian. But now the devil is, how can such a Hamiltonian be realized in some simple system which is experimentally accessible? So there are already several proposals around 2011 for different kinds of ways of realizing these higher spin Dirac Hamiltonians. But at the time, the existing proposals were quite tricky to implement. You either need to have a multi-component optical lattice with some specially fine-tuned spin-dependent hopping, or you need to do stacked 2D materials, or you need some lattice which is very fine-tuned to achieve this threefold band crossing point. So we were interested in finding simpler ways for achieving these generalized Dirac Hamiltonians. So first of all, we found that the spin 1 case could be relatively straightforwardly implemented using this kind of square lattice structure, which is now called the Lieb lattice, which involves taking a regular square lattice and removing 1/4 of the sides. If you do so, you'll get a system with the following band structure, which has the 3 bands touching at the corners of the Brillouin zone. in a similar manner to the case of graphene, you can do a long wavelength expansion to get an effective Dirac Hamiltonian. And in this case, this Hamiltonian involves spin 1 matrices rather than spin half matrices. But otherwise, all the conclusions for graphene still hold. So similar to the case of graphene, there is a conserved total angular momentum, which is a sum of this pseudospin term and the regular orbital term. One of the peculiar differences for the case of spin 1, of course, is that we can have different magnitudes of the spin projection onto a given axis. So the projection can be non-zero or zero. So this gives rise to qualitatively different wave packet dynamics depending on whether the spin projection initially is zero or non-zero, which is shown here. So for this, these images are experimental data taken in collaboration with a group in Germany, where they fabricated this structure as a waveguide array, and they were able to observe the conical diffraction of different pseudospin states at this generalized conical intersection. Okay, so this was published in 2016. Okay, so moving on. What about even higher values of the pseudospin? Now, honestly, at the time, this seemed to me like it would be impractical to do. You need to engineer a degeneracy between 4 or more bands, which seems like it would require a very complicated fine tuning or some lattice which is very impractical to implement. So in the following years, there were a few proposals for doing these higher values of the pseudospin, but the models, in my opinion, were a bit too complicated to be feasible. And then in 2020, this very interesting paper came along. So here the authors provide a way to systematically generate high degeneracy conical intersections that are, firstly, they are protected by sublattice symmetries. And secondly, the lattices that get out of this take a relatively simple form, which is amenable to implementing in experiments. So the basic idea is to start with a permutation symmetry matrix, which encodes the degeneracy of the desired order. This permutation symmetry matrix can then be mapped to a graph, which can then be embedded into a periodic lattice of a desired dimension, like so. So this gives a systematic way to get a lattice out of the desired order of the conical intersection. So in particular, they looked at the case of the spin 2 conical intersection. They showed that it could be realized with this particular hexagonal lattice structure, which they call a chiral graphene. So it has been predicted to exist as a two-dimensional material under certain conditions if you use as a planar sheet of boron atoms. And in this case, the band structure in the type binding model has a 5-fold degeneracy at k = 0. So I was unaware of this paper until my former collaborators in Germany, they bumped into one of my students at a conference and mentioned they were working on this and needed some help with interpreting their experimental results. So then we started collaborating again after several years. So they fabricated this graphene lattice as a waveguide array, which is shown here. which has the following band structure with the 5 bands touching at the k equals 0. As I mentioned, since this is a case of a spin-2 conical intersection, there's a flat band sandwiched between the conical bands. And this flat band is associated with special non-diffracting states, which I don't have time to go into today. What I think is more interesting, and the smoking gun of this higher order conical intersection, is the potential to generate higher charge phase singularities via conversion between different pseudospin eigenstates. So in particular, if you excite this conical intersection with a pseudospin -2 initial state, conversion from pseudospin -2 to +2 will be associated with the generation of a high charge, a charge 4 phase singularity, which is shown in this series of panels here. So in this case, the initial state has pseudospin +2. And so the output in this component has a flat phase profile. And then as you look at the projections onto the different output pseudospin components, you see the phase singularity, phase singularities of different charges from 1 to 3 and 4. But similar to the case of the graphene lattice and the Lieb lattice, we have a total angular momentum which is conserved at this higher charge conical intersection, suggesting that it perhaps could be or could serve as a microscopic model for spin-2 particles, such as gravitons. So this brings me to the end, and this is the most recent result we have published last year. Before concluding, I would like to thank my collaborators over the years on these works. So particularly my PhD supervisor, Anton. Omri, who was a postdoc who worked on the honeycomb lattice results. And our experimental collaborators at Münster University in Germany, which divided into 2 groups. The first group who looked at the Lieb lattice in 2015, 2016, and then the next batch of students who studied this chiral graphene lattice. So conclusions. So I think these conical intersections are very interesting as a way of having a tabletop analogs of phenomena from high energy particle physics. Raises interesting philosophical questions as to whether space-time is continuous or discrete. The more recent results, which I presented, show that it is actually feasible to implement higher spin conical intersections in an experiment. And this opens the possibility of exploring interesting analogies with charge, or with spin-2 particles such as gravitons. This, I think, is a very interesting direction for future work. So if you want to know more, then we have several papers published on this over the years, including a review article, but this is, I guess, out of date by now. So with that, thank you for your attention, and I'm open for questions.
Oh, thanks, Daniel. That was very, very interesting talk. I don't see any questions in the Q&A panel just yet, but I had a couple of possible questions. I mean, you mentioned the sensitivity to small perturbations is explained in terms of large changes in the Berry phase. So yeah, what does that have? What would be the implications of that in terms of practical materials? For example, if you have a lot of edge dislocations or grain boundaries or things like that, is that how sensitive would the system be to those sorts of distortions, or even go all the way and imagine some sort of glass-like structure? Would everything fall apart, or what would happen?
So I think in the case of electronic materials,
Yeah.
you would not see this very strong sensitivity because if you have a very small gap, thermal fluctuations will smear out the Berry curvature effects, and you won't see this. But for the case of photonics, where we can actually excite this single band efficiently, there are no temperature fluctuations we have to worry about, and so it will be possible to resolve these large effects due to small perturbations.
Right. And my second question was, so in relation to the analogy that you're drawing with the gravitons, how far have you taken that work? Have you reached the point where you could make some tentative predictions about the behavior of gravitons, which you might not have anticipated if this analogy is strong enough, or is it embryonic at this stage?
It's very embryonic. So in the papers which were published in 2023, we even didn't want to mention these analogies because there are some complications, like
Right.
so like in the case of conical intersections, you can have any projection you like of the spin onto some axis. But for gravitons, I think some projections are forbidden.
Right.
But I think the next step would be, as you mentioned, you take one of these lattices, you then introduce controlled perturbations like strain or a topological defect.
Yeah.
This will be visible as an effective gauge field in the evolution equations, and this would be a
Right,
first
of course,
step
yes.
for looking at these analogies.
Right.
So this kind of procedure was done for graphene, definitely. For the Lieb lattice, probably, but I'm not aware of the reference off the top of my head. So I think similar methods should work for this Borofene lattice.
There's a question from Zimin Lee. He says, what are the most important differences between conical intersections, twofold generacies, and higher order conical intersections, three and morefold degeneracies?
So for the case I mentioned this additional flat band for the case of the integer spins, and this is very interesting separately because in a flat band you have vanishing transport. This gives rise to strong sensitivity to perturbations such as interactions and so on. From a practical point of view, one important difference is that for the spin half intersection, it can be symmetry protected. So in the case of graphene, if you have the inversion symmetry, you are guaranteed to have this conical intersection by symmetry analysis.
All right. Yeah.
Generally, for higher order intersections, they are not protected by symmetries. So if you, I don't know if I have it here. So yeah, even for the case of this threefold degeneracy, if you zoom in very closely, you will find there is a small but non-zero gap between these bands. This gap cannot be eliminated by symmetries. You have to fine tune to minimize it, which we can do in photonics, but it perhaps makes it more difficult to needs to be taken into account. Okay, but now that I mention it, I recall you had a seminar, I think, talking about doing this kind of lattice for atomic systems. So there are ways to fine tune to avoid this gap opening as well in electronic systems.
Very interesting. And then Zemin had a follow-up question. Would the geometric phases or other physical properties be substantially different in twofold or higher fold conical intersections? I think you might have just touched on that a little bit.
Yeah, so but because it's not like in the Lieb lattice, the geometric phase is 2 pi, but it's equivalent to 0. So I think this ties in with this lack of protection of the degeneracy. Despite this vanishing Berry phase, you can have non-zero Berry curvature when there's a small gap, and still non-trivial geometrical properties.
All right, well, that's it. Well, that wraps it up. There aren't any more questions that I can see. Thank you very much, Daniel, for a really interesting talk. You're going to watch the video again with interest. I'll just remind everyone that the Daniel's talk will be available on YouTube within a few days. If you wish to follow up and look at it again, I certainly will be. Thank you once again, Daniel, for a very, very interesting talk, and all the best.
Thanks for the invitation to speak.
So you're most welcome, and thank you everyone for attending, and we will let everyone know when the next talk is happening and what it's about. So good afternoon, everyone, and we'll see you again. Bye for now.